And go.
So, David is going to be presenting about sigma pi diagonal 1 alkyne complexes and how they participate in ene reactions. There we go. So, these are the reactions that gold-1 catalyst, that they were looking at, that gold-1 catalyst catalyze. And they're cycloisomerizations with an alkyne and an alkene. And so they cyclize to give you a ring with just an alkene, and you leave the other alkene alone. So this, for the most part, stays, and this alkyne loses one pi bond, and it binds that carbon, and you get a ring. And so they did that with this starting compound, and then this one. And they used, well, I guess we'll get to it, but they used okay, there they are. So they used these gold-1 reagents, but they also formed the digold versions of them as a converter. That's it. So what are the sigma pi digold complexes? So you start out with the normal gold-1 reagent, and that's just a gold ion that it has a ligand, and it's also coordinated via the pi bond of the alkyne. And then it converts to being sigma bonded, and then the other gold reagent, usually the same one from the first one, comes in and coordinates on the pi bond. And then you get the digold reagent. And that's the ones that they actually use. So they used this one for that first reaction to make the cyclopentene, and then that one for the andine molecule. And so the main purpose they were doing this experimentation is to figure out if digold complexes actually participated in this catalysis, or they were a dead end. And long story short, it's a dead end. But so this is the proposed mechanism by which digold would participate. And so they, like the earlier papers said that, so you get this digold reagent, then a geminal digold intermediate, and then that funky looking thing, and then you lose your gold and you get your product. But they did a lot of tests with reactivity tests. So this is just the results of that. But so what they did were they did the reactions with the regular gold-1 reagents, and they got their yields. And then they tried doing these reactions with the digold reagents, like they synthesized them. And all you have to do really, from what I've read, is just leave the gold-1 reagent alone long enough, and it will form these digold reagents. I think they had to do something special to isolate that. Didn't get that far into it. But so when they did these reactions with just pure digold reagent, nothing happened. And then they tried to heat it up, nothing happened. And then when they were doing these reactions with the pure gold-1 reagents, they changed the counter ion to this borate thingy. And then when they did this, they reduced the formation of digold complex and then increased their yield. So that leads them to think that these digold reagents are harmful to the reaction. And so what they actually found, okay, I didn't include that. So they did a bunch of thermodynamic tests, and I think they were doing the delta G's of these complexes to see what were more stable compounds, and these digold reagents are more stable, so they're less reactive. And that's what they are proposing happens. These digold reagents form after a while, and they're too stable to re-enter catalytic cycle, and it just kills your reagent. And that's about it.
Yay! Could you back up a couple slides? One, go forward maybe. Yeah. So when you have 81 to go to 82 there,
Yes.
where the gold inserts,
Mm-hmm.
Where does our nice little hydrogen go? That should be off at the end of that alkyne.
I don't know.
Okay, I'm just wondering.
I mean, maybe the counter? something? I don't know.
Okay. And if you go forward one slide to the, one more. There's a very specific reason why they use that ion, which I won't tell you. You'll be able to figure it out as we go through the semester. But you call that barf.
Yeah.
Well, yeah, why is there an F minus, like, what's the F minus?
I have no idea. What was that? That was weird.
I'll leave that for David as well. The F talks about how the aromatic ring is substituted.
Oh, okay. It was an argon borate complex.